Turbulence in a pipe is a predictable physical state, triggered once a flow crosses a specific, measurable threshold. The state depends on a conflict between two forces: inertia, which drives the fluid's momentum apart, and viscosity, the internal friction trying to bind it together. To calculate which force is winning that battle, engineers use the Reynolds number. This diagram maps the Reynolds equation against three distinct zones: laminar, transitional, and fully turbulent. The numerator, density, velocity, and diameter, contains the inertial drivers. When these variables increase, they push fluid into the turbulent zone on the right. The denominator is dynamic viscosity, the stabilizing force. High viscosity keeps the fluid locked in the smooth, laminar zone on the left. This creates an AEE exam shortcut. As velocity or diameter increases, the inertial numerator takes over, guaranteeing turbulent flow. Conversely, if a fluid has extremely high viscosity, the denominator will dominate the ratio. This ensures the flow stays laminar, regardless of the pipe's physical size. The Reynolds number identifies if turbulence exists. However, calculating how that turbulence behaves requires a different set of mathematical models. In a turbulent state, tracking the instantaneous velocity of individual particles is impossible because of the chaotic nature of the eddies. Osborne-Reynolds modeled this by splitting velocity into two parts, a constant mean velocity and a fluctuating component. Note the definition for isotropic turbulence. If the mean square of these fluctuations is equal in all directions, the flow is isotropic, a frequent exam objective. This intense lateral mixing between layers creates a massive apparent shear stress. In turbulent systems, this momentum transfer becomes the primary source of resistance, while standard viscous friction becomes negligible. This represents the total shear stress equation, the mathematical sum of standard viscous and powerful turbulent shear. In Boussinesq's equation, unlike fixed dynamic viscosity, eddy viscosity changes based on the turbulence intensity. While Boussinesq provided the theory, engineers still needed a way to link this macroscopic mixing to measurable velocity gradients. This diagram illustrates Prandtl's mixing length hypothesis, bridging the gap between chaotic mixing and measurable flow. The mixing length, L, is the average transverse distance a fluid parcel travels before transferring momentum to a new layer. By using these macroscopic mixing lengths, engineers can calculate fluid resistance, even when microscopic viscosity is no longer the dominant factor. Constant lateral mixing pulls fast-moving fluid from the core toward the walls, which homogenizes the speed across the pipe's center. This graph compares the two states. The traditional parabolic profile of laminar flow is replaced by the flatter, turbulent logarithmic profile. To normalize these equations, engineers use shear velocity as a critical scaling parameter. While the core is turbulent, we must look at the boundary wall. Here, the fluid velocity drops to zero due to the no-slip condition. Near the wall, velocity is so low that viscous forces overpower inertia, creating a microscopic, purely laminar film hugging the boundary. The formula for this sublayer's thickness reveals an inverse relationship. Faster core flows mean thinner films. Pipe classification depends entirely on how the physical roughness peaks of the wall interact with this microscopic laminar sublayer. This topography diagram contrasts boundaries. On the left, a smooth boundary has a roughness ratio below 0.25. The sublayer swallows the peaks. On the right, a rough boundary ratio above 6.0 means roughness breaches the sublayer, significantly increasing friction. In short, the physical texture of a pipe only impacts the mathematical resistance if it is tall enough to pierce through that protective laminar film. These topographical boundaries determine which empirical formulas are required to calculate the friction factor, F. This slide shows the Blasius formula, which is used strictly for pipes classified as hydrodynamically smooth. Note the dependency checklist. If a question defines the flow as smooth, any roughness value provided is a decoy. For smooth pipes, friction depends only on the Reynolds number. When the flow velocity increases and the laminar sublayer is destroyed, the pipe is reclassified as hydrodynamically rough. This is the formula for rough pipes. In this state, resistance is dictated by physical collisions between the fluid and the wall. In this case, the Reynolds number is irrelevant. Friction depends entirely on the relative roughness of the pipe. This chart, Moody's synthesis, consolidates these individual empirical equations into a single graph. In Zone 2, the smooth turbulent region, we see the downward-sloping Blasius curve, where friction decreases as the Reynolds number increases. In Zone 3, the fully rough turbulent region, the lines go flat. Because the sublayer is gone, friction is tied to the physical wall texture, and further increases in velocity no longer change the friction factor. These flat lines prove that, at extreme velocities, inertia renders viscosity irrelevant to pipe friction. Let's look at how the APPSC AEE exam tests these boundary layer concepts in a typical objective problem. Examiners rarely provide these clean formulas. Instead, they mask the correct answer by unpacking the variables into their foundational base terms. This slide shows a scenario asking for the algebraic expression of the laminar sublayer thickness, delta. First, you must unpack kinematic viscosity into dynamic viscosity over density. Next, you unpack the shear velocity into the square root of shear stress over density. By performing the algebraic substitution, you reveal the complex final expression that actually appears in the multiple choice options. Knowing how to unpack these base variables prevents examiners from hiding the correct answer behind complex algebraic variations.